Hello everyone, we are in the Chernobyl RBMK reactor simulator from simgenics, and following the suggestion of Comrade 757 Spy, I will do a power down of this reactor. We can have a look at the state of the reactor now. We're at 30% of power set point. I don't start at 100% power set point because even a kindergarten kid can power down this reactor from 100% to 30%. So the tricky part starts when we go below 30%, that's why I start the video here. And we can also look at the thermal power slightly below 30, it's at 28.4%, and this yields almost 200 megawatts of generated load in the turbine generator. Now I just set the turbine into manual mode with an aperture of the main valve of 26.7, and this is slightly and slowly increasing the drum pressure. So now to start reducing power, I will switch back to auto, and I will manually set the pressure set point a bit lower than that, maybe 7500, but 7600 would be also fine. And now we see instantly the generated load increasing to 220 megawatts to release this accumulated power in the steam pressure. So now we can already start decreasing power set point. I will go to 25%. Okay, and everything looks fine to me. We should keep an eye into the turbine temperature of the rotor and the shell. We don't want to get too high differential between the two. I will continue powering down by decreasing power set point. Now let's go to 20. And looking at reactor level, we have a rather low reactor level. This is because we are reducing voiding, so the overall volume of the reactor, so the mix of water and steam, it's being reduced because of the reduce of voids, and that's why there is a decrease of reactor level. But apart from that, everything looks stable. The generated load is at 58 megawatts. We can continue going down to 15%, and then we will stop at 15%. Now we will wait just a bit to let things stabilize, in particular the generated load, because now this will be a critical point. We don't want the generated load to go down to zero, because if it goes below zero, we can have a negative or reverse load. It means the grid is giving power to keep the turbine spinning, and if this happens for more than few seconds, the turbine will trip. So this is something to avoid. Okay, this thing looks like it's stabilizing at 36 megawatts, power set point 15, and the feed water pumps are set for a power higher than 80 megawatts, which is 3 pumps, 3 element control here, and main valve. So we can start switching things to feed a power below 80 megawatts. I advise to do first the switch from main to startup valve in the turbine. So I will do it now, but keeping an eye into the generated load. If this starts decreasing and gets close to zero, I should immediately do something to avoid it. So pressure set point is set to auto to keep this value, and now I will switch to startup. Okay, startup is opening, at the same time the main is closing, and the generated load goes down to 9.6. Okay, so it stabilized at it went down to 6, and now it's going back up to 20 or something. We'll wait a bit for this to stabilize. We also see the spike or the dip that it made in the reactor level. I guess this is because the opening and closing of the two valves is not in perfect synchrony. So one starts closing before the second starts opening or something like that. Generated load, it's higher than before, it's at 113 megawatts, but it's oscillating, so we'll wait a bit for it to stabilize, otherwise we could incur into a reverse load. the oscillation is quite huge. It went up to 100 megawatts and down to 12. Okay. So now I will slowly reduce a bit power set point, maybe to 13. And it doesn't seem it will go above 80 megawatts again. It seems it just stabilized around 30. So now I will start rolling back the systems to the position for less than 80 megawatts. I will switch off the pumps 2 and 3, the feed water pumps, and close the discharge valves. I will let the inlet open in case I need to turn on one of the pumps quickly because of some reason. I will switch from 3-element control to 1-element control in the hot well level and switch from the main valve to the startup valve in this same system. Generated load at 16 megawatts. That's fine. Now we go to the turbine support system. Lube oil, hydraulic pressure and steam seal are fine. We can only stop the steam seal once the turbine is stopped, so we can never stop it while running. We need to, or we can open the steam drain now. So I open the steam drain. Generated load went up to 60 suddenly, but I guess it will stabilize back to some other value. So we already disconnected 2 of the 3 feed water pumps, turbine in the startup valve, jump level control 1 element and startup valve. So we did everything we needed to disconnect the generator. Now I will continue reducing set point to 10%. And once things stabilize, I will need to open the generator brake to go off grid, so disconnect the generator from the grid. But this will be a very critical point, so to prepare for this point I need to reduce the power set point in the main steam dump control system to just above what it is now. So it's at 7500, let's set it at 8000. So once I go off grid, we'll have a lot of power from the steam that we have to direct from another place. So this will go to the relief valve of the main steam dump control system. So this will open the valve when the pressure goes above 8000. It makes no sense to put it higher because we will just waste steam energy. Sorry, we will not waste steam energy, but we'll just go higher in pressure in the drum without any reason, because now we want to power down, so I think 8000 is a good number here. Okay, generated load stabilized at 12 megawatts. Power set point is at 10%. And now we will switch to manual. And we will start closing the valve manually. Slowly. Why this? Because if we are at a generated load of 12 megawatts and we go offline by opening the brake, it's like if we are driving in the highway at a constant speed with the car, so the engine is at a given load given by our throttle, or if we have like cruise control by the computer that controls the throttle, and then suddenly we just press the clutch. If we don't change the load and we press the clutch suddenly, the engine will rev up and will brake or go to red line in a very few seconds or milliseconds. So here it's the same. If we just go offline and the load is the same, so it means the valve it's open at 26%. The turbine will spin up to like 37, 38, 100 RPMs, and it will break down because we will not be able to close the valve on time. So now I will reduce manually the valve opening until we get a generated load close to 0. It means we have very few excess power to spin up the turbine once we go off grid. So I know the value when the generated load is 0 will be an opening more or less of 6%, because this is the opening of the valve to keep the turbine spinning before connecting to the grid, before synchronizing. So this is the more or less the load that we need to spin it freely. Like if you were accelerating in a car just to keep the engine running in idle or in neutral in the gearbox. But we should be very carefully, because as I said before, if we go below 0, we will have a reverse load and this will cause a turbine trip. So let's continue, but keeping an eye on the generated load and the startup position. We're at 1.6, so very careful now, and we can also see that the main steam dam control is already opening the valve. Once we are below 1, we can already open the brake, but the closer we get to 0, the better for the turbine, because we will not spin up too much above 3600 RPMs. So I will close just a bit more, and we're at 0.5 megawatts. So this is the power that will spin up the turbine now when I open the brake. I will open the brake now, and immediately I will close a bit more the valve. So I open it, and you see the speed going to 36.0405. So I need to decrease a tad more. Let's decrease it to 3.9. And now you see that the speed is decreasing. 3600, 05, 04, 03, etc. I will just turn off the oscilloscope because it's annoying. And now we need to spin down the turbine. We cannot just close to 0 the valve, because this will alter a lot the shell and rotor differential temperature, and then we'll have a differential expansion too high and the vibration will be very high. So I will start closing the valve slowly while looking at the temperature of the shell and the rotor. Now the set point of the drum is kept at 8000 by this 10% power from the reactor, and this is the pressure that drives the steam to slow down the turbine smoothly. So we see shell and rotor decreasing temperature almost in synchrony. We can decrease a bit more the startup valve opening. They are almost still in synchrony. But once we get to a very low discharge of steam, if we close a lot the valve, this temperature here, the entrance steam temperature, will also decrease, and then we'll start getting problems. So I will decrease a bit more to 1.9. Shell and rotor are still at a very equal temperatures. But now we see the entrance temperature is very low, is 116, and being low and lower, becoming lower and lower. I will close a bit more the startup valve. And now we see how at this opening the rotor temperature starts increasing, because it's not cooled down enough by the steam temperature. You see that now the steam is cooler than the rotor, so the steam is cooling down, not heating up. I need to reopen a bit. Let's reopen at 1.9, and you see that the rotor is decreasing temperature again. So I will keep this valve at 1.9. The vibration is a bit high, but still on the acceptable range. And I will start decreasing a bit the power in the reactor. We could just keep at 10% the reactor while spinning down the turbine, because the main steam dam control relief valve is taking care of this, keeping the pressure in the drum constant, but this 18% of opening is just energy that we are wasting. So as far as this doesn't close to zero, which means the pressure in the drum could start dropping, we can reduce the power set point of the reactor. So I will go to 8 and wait for a while for things to stabilize. Okay, the relief valve is closing. It's at almost 10% now. So I will close or reduce a bit more the power set point. Let's go to 7. Relief valve at 9%, 8%. We can see here with 1 decimal point. 6.9, 6.5, and I think we will get close to 0 without closing it totally, so it looks to me like a good value, 7%. I think I will try closing again a bit the turbine valve to see if we create vibration or not. Now both the shell and the rotor are at very low temperatures, like almost ambient temperature, so there is not a big deal anymore, I think. The speed of the turbine is at 2400 now. The relief valve is at 5.3%, so I will close a bit more. I will reduce a bit more the power set point, 6.5%, to see if we can get close to 0, just to save energy. We got a bit of vibration now. It seems that the shell cooled down more than the rotor. I will try to go a bit further in the closing of the valve, but I think this will be too much. No, that's fine. 2100 RPMs and slowing down more and more. Relief valve at 3.6, so I will try to reduce reactor power to 6%. And even if it goes to 0, I will not worry too much, because the turbine is at a very low speed already. Well, not very low, but like at half of the spin down. The valve is almost at 0% of opening and we don't get vibration, so we could already close totally the valve. I think we don't need pressure in the drum anymore. So now I will reduce the set point to 7500, so I can reduce power set point a bit more to 5.5%. And I will try to close the valve totally. Now the valve is at 0%, the turbine is just freely spinning without any admission of pressure or steam. And because the steam seal is still on, this means that there is a vacuum in the admission or the inlet of the turbine that is breaking it down. So it's not just breaking down because of the friction, it's breaking down because the thermodynamics of the admission makes it break down, because it has a negative pressure now. Shell temperature at 27 degrees and rotor at 43, so this is almost ambient temperature. Okay, vibration is decreasing, it's at 42%. Drum pressure at 7400. And it's increasing, so I can decrease reactor power because now we will not need the drum pressure anymore. The turbine is just spinning down by itself. The relief valve is close to zero now, so now we will start decrease of the drum pressure because of reactor power decrease. Very good, the turbine is spinning down by itself. I think we don't need the reactor anymore, so I will reduce the power to 2%. So below 2% we are ready to switch off the automatic reactor control and shut down the reactor totally, inserting absorber rods here in the absorber rod control and fuel monitor panel. And then we can just start switching off all the other elements in the secondary circuit and water treatment pumps. Now the steam pressure is being reduced, so we need to shut down the reactor. It cannot be running at 2% with a too low pressure. This is not by the book, so I will switch off automatic reactor control and keeping an eye on the trend chart to see what happens. Why the neutron rate is negative now? Maybe it's because of the reduction of pressure. So I will switch it off, the automatic control, and now I will insert rods. I will hold, this was a bit too fast. I will, oh no, it's in the slow mode, so it's okay. I will insert rods. And we see here this indicator, -2, this in a log scale. So if it's like -10 or -20, we can consider the reactor is shut down. Thermal power is still 0.3% because of the decay product. So we'll need some systems to cool this down, even if it's from a neutron standpoint shut down reactor. The turbine is below 1000 RPM, so very close to total stop. Control rods are at 40%. They are so much withdrawn because we have quite a lot of poisoning. We have 190% of xenon, but this is because we come from a shutdown previous to this simulation. So you didn't see it before, but I was in a shutdown state. I ran the reactor up to 30% power, and then we started this video. So that's why we have such a big poisoning. I think it's time to start the offline core cooling system. So I will start the loop 1 and loop 2 pumps. Okay, and I will open the outlet valve. This will start the flow of water to cool down the reactor. I remind you this is just because of the decay products, because the neutron power is already very low. So what is it saying here? Yeah, that's fine. So I will reduce power set point now to 1000. Turbine is in turning gear now, so I can switch it off here. And you see when it's in turning gears at 20 RPMs, it's like an electric motor that keeps it rotating to be ready to spin up. And when we switch off this gear, then it just spins down to 0 RPMs. The offline cooling is working well, so I close this window. We don't need the emergency cooling anymore. I will leave it on for a while because we still have 0.2% of thermal power. because of the decay products. We also see the drum pressure going below 1000 because of the cooling. And now that the thermal power starts to be really low at 0.2%, we can stop the feed water pumps. Okay, switch off this pump, close the discharge valve, and I will also close the 3 inlet valves. The condensate system we can also switch off. I forgot to switch off the second pump. We could have done this when we were at 15% of neutron power, but anyway. Switch off this, set the deaerator level into manual, and set the polishers out. We got the alarm for the trips. Okay. Condenser vacuum and the aerator pressure. I will break the vacuum breaker. I will open it. But first, I think I need to stop the steam seal from the turbine because it's already at 0 RPM. So I stop the steam seal. I open the steam drain, and we already see the condenser vacuum going down. I close the steam drain. I stop the hydraulic pressure, and I stop the lubricating oil. So all the systems of the turbine support are off. The condenser air ejector is off because we don't have pressure in the condenser. And I open the condenser vacuum breaker, but okay, now it's open. Good. Turbine trip because I disconnected all the turbine support systems. This is good. I set this into auto, and I will close the aerator vent valve, so it needs to go to 0%. And the thermal power is 0.2%, so still something to take into account. We cannot stop the offline core cooling systems. Rods are already inserted at 100%, and we have an activity in the log indicator of minus 87% in the neutron flags. The aerator vent valve, oh sorry, I almost destroyed the microphone. The aerator vent valve is at 0%, so that's fine. I think I already did everything. I will acknowledge these things. Okay, the feed water, no, sorry, the water treatment pumps. I will stop the 2 pumps and close the valves. I also have pumps in the primary, loop 1 and loop 2. I will switch off the pumps and close the outlet valves. Also the inlet. Okay, so everything is closed. And I got the alarms for the trips, that's fine. And we still have the condenser circulating water pumps. I'll switch off these 2. And now everything is off except the 2 offline core cooling systems. So reactor at minus 88, shutdowns situation. We still had 89% of fuel remaining. Turbine is at 0, in trip position. I close this window. The main steam dam control, I set the valve at 1000, but we are already at 0 pressure. I will switch to manual and close this window. The reactor is with the automatic control off, the auto scram control on, but we don't need it anymore because we're in shutdown, so I switch it off. I close this window. We got some alarms here, but this is normal. Here turbine, the temperatures are like ambient temperatures at 22, 23 degrees. I close this. The drum has no pressure and the water is at 65 degrees. The reactor fuel elements are at 58 degrees in both sides, and we still have a thermal power of 0.2%. So we'll need to run the offline core cooling systems for a long while until we reach 0% of thermal power. Maybe I will disconnect the emergency diesel pump, so I will close it. And we got here the alarm that the emergency cooling system is not in auto. The aerator is set into manual. Condenser hot well, I didn't touch this at all. Water treatment, it's off. I will just open this schematic once more to show that everything is off. So it's the green colored pumps, except the 2 offline core cooling systems, and that's all. It took us half an hour to shut down this plant, starting from a 2 megawatt electric power, which is like 25% or 20 or 25% of the nominal, and that's it. I hope you like this video. See you in the next. Bye.